Hello and welcome. In the last video, we talked about evaluating limits that result in indeterminate form by using factoring and conjugates. In this video, we're going to talk about important trig limits and tricks to use when trying to evaluate limits involving trig, typically that result in indeterminate form. And then we're going to wrap up this lesson by talking about the squeeze theorem, which is a theorem that comes into play quite often when we're dealing with trig functions and limits. So some important limits that you should know, and in a different video I can prove these to you, but you can use these as fact. The limit as x approaches 0 of sine of x over x is equal to 1. And there's a great proof involving some geometry that can come into play, but today we're really just going to focus on how to use these identities and other trig identities to benefit us. The second limit that you get to know, or importance to know, is the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. And the last one, which we're actually going to derive in this lesson, is the limit as x approaches 0 of tangent of x over x is equal to 1. Some things to remember: using these three trig limits that you can just use, sometimes it's helpful to manipulate something to look like one of these three. Another thing to remember is that oftentimes using little things that you learned in other classes, such as the fact that tangent is sine over cosine or any other reciprocal-like identity, may help you manipulate in a way that gets you to the limit that you're looking for. So if I look at this limit down here, the limit as x approaches 0 of 3 sine of x over x, I can't use direct substitution because that would result in indeterminate form. What I can do is I can take this scalar out based on the properties we discussed in the last video, and this would become 3 times the limit as x approaches 0 of sine of x over x, which we just said up top, this limit here is 1, so this is going to become 3 times 1, which is 3. Well, what happens if we have something that looks similar to this property, but not exactly the same? That's sort of a sneaky looking at this one down here. The limit as x approaches 0 of sine of 3x over x. Well, wouldn't this be nice if either that 3 wasn't in the numerator or we had a 3 in the denominator? That would make this limit really give us what we need, which is that this would go to 1. Well, I can put a 3 there as long as I put 1 in the numerator, because what I have done is changed this limit by multiplying it by 3 over 3 or multiplying it by 1, which means that I can take 3 times the limit as x approaches 0 of sine of 3x over 3x. This goes to 1, so this becomes 3 times 1, which is also equal to 3. So be on the lookout for things that look like sine of x over x and how you can manipulate to get them to be what you want them to be. The other thing to be on the lookout for, and yes, we actually already know the answer to this one over here, it's going to be 1, but let's justify that using something else that we know. So we know that tangent is the same thing as sine over cosine. So this is really the same as the limit as x approaches 0 of sine of x over x, this x, times cosine of x. Now, if you think about properties of limits, we're actually allowed to split this up. So I could rewrite this as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. Well, this limit right here we know is 1 from over here. I can use direct substitution on this limit because cosine of 0 is negative 1. Sorry, cosine of 0 is positive 1. So if I just evaluate this limit using direct substitution, I get 1. And 1 times 1 gives me 1, which is what this identity up here had showed us as well. Why don't you pause the video and see if you can work through number 2. Try manipulating sine or tangent in a way that might help you use one of these 3 properties up here to get to the answer. And then unpause the video and see how you did. Okay, well, I'm going to rewrite this. The limit as x approaches 0 of sine of x over x, since x squared is just x times x, and this, so all I've done so far is I took one of these x's out and I took this sign, so what's left is tangent of x over x. Well, I'm going to split this into two separate limits. The limit as x approaches 0 of sine of x over x. We know that this limit is just going to be 1 times the limit as x approaches 0 of tangent of x over x. We know that this limit is also just 1. So the product of those two limits is going to be 1. So I'm hoping that you're starting to see what we're doing in these problems is we're manipulating the limits, manipulating sine and cosine and tangent in ways that we can use those top three trig identities. Let's look at some more practice problems. Don't forget that the first thing you should always try and do when you're looking at a limit is use direct substitution. And on this problem, direct substitution is going to work just fine. If I put pi over 6 in here, I don't have any issues with indeterminate form. So sine of pi over 6 minus pi over 3. Well, pi over 6 minus pi over 3, I'm going to rewrite this with common denominators. Pi over 6 minus, if I multiply this by 2 over 2, I get 2 pi over 6. This is going to become sine of negative pi over 6, which means instead of going clockwise to get to pi over 6, I'm going to go counterclockwise to get to negative pi over 6, and that's going to give me negative 1/2, since this point would be root 3 over 2, negative 1/2 on the unit circle. All right, on number 2, let's see if direct substitution works. Doesn't seem like we're going to have any issues with indeterminate form, so I think we're going to be okay here. Remember, you can use limit properties, so we can actually say that this is the limit as x approaches pi over 2 of cosine of 2x, and we can put the limit to the power of 4. Now we can use direct substitution on the inside, so this is going to be cosine of 2 times pi over 2, so cosine of pi to the power of 4. Cosine of pi is negative 1. Negative 1 to the power of 4 is positive 1. Go ahead and pause the video and see if you can work through number 3 on your own. All right, I'm hoping that you notice that this is exactly like one of our trig limits, except there's a 5 there, but I can move that 5 out front. 1/5 times the limit as x approaches 0 of 1 minus cosine of x over x. This limit is 0. 1/5 times 0 is just going to be 0. Let's look at some more practice problems. I'm going to encourage you now to push yourself, pause the video and see if you can work through these final 3, and then unpause the video and see how you did and work through them with me. Okay, number 4, I'm going to get indeterminate form if I directly substitute in. So now I'm going to try and use trig identities. So the limit as x approaches 0, the first thing I notice is that sine over cosine could be rewritten as tangent. And then there's still this x in the denominator, and this is one of our trig identities that gives us 1. On number 5, I don't want that 5 in here, so I'm going to pull a 5 out. I'm going to say 1/5 times the limit as x approaches 0. If this is sine of 2x, what I really want is 2x in the denominator, but the only way to get that is if I multiply this by 2 over 2. So I'm going to put this 2 out front with the 5. So now I have 2/5 times this limit, and this limit is going to be 1. That's our sine identity, and that's going to give me 2/5. And then on number 6, this one is definitely a more challenging one. What I'm going to do first is I'm going to rewrite tangent as sine over cosine. The other thing I'm going to do, because I'm going to run out of space if I don't, is instead of writing divided by sine x over cosine x, or sorry, divided by sine x minus cosine x, I'm going to write multiply by 1 over sine x minus cosine x. So now, what I want to do, this should not be one big long fraction, there we go, is I want to find a common denominator here. So I'm going to multiply this side by cosine x over cosine x. So I'm going to have the limit as x approaches pi over 4 of cosine of x minus sine of x all divided by cosine of x. So that's what this has become after finding a common denominator. I'm multiplying that by my 1 over sine of x minus cosine of x. So now these two things look the same except their signs are opposite, which means you can simplify them, and instead of getting positive 1, you're going to get negative 1. So if I simplify these two things, I'm going to get a negative. So I'm going to get the limit as x approaches pi over 4 of negative 1 over cosine of x, which means now I can use direct substitution. This is going to be negative 1 over root 2 over 2, which means I'm going to take that reciprocal, and that's going to simplify to just be negative root 2. And if you don't rationalize the denominator there, that would simplify to be negative 2 over root 2, which is also a totally acceptable answer. So that's where we're going to stop with those trig identities. What we're going to do to finish off this pretty short lesson is we're going to talk a little bit about the squeeze theorem. The squeeze theorem basically says that if we can't find a limit, but we can trap it in between two limits, we may be able to gain more information about the thing we don't know the limit of. So if we could say, I don't know what the limit of h of x is as x approaches c, but I know something about two things that I can trap it in between, that may help us find the actual limit. So our goal here is to trap a limit we don't know between two bounds. And this comes into play quite a bit with trig because we know that sine and cosine oscillate between negative 1 and 1, which means we know sort of an upper and lower limit. So we're just going to work through one example so I can show you how the squeeze theorem works. Then we're going to recap what we covered in this lesson, and then we will be done. So if I was trying to evaluate this limit here, right now I can't use direct substitution. There's not some special trig property that helps me with sine of 1 over x. So what I need to do is find a different way to trap this in between two things that I do know. So what I want to start with is that I know no matter what I'm doing, if I'm talking about sine of anything, that is going to be trapped between negative 1 and positive 1. So even if this is 1 over x, no matter what I'm taking the sine of, the highest it can be is 1, and the lowest it can be is negative 1, since there's no vertical stretch or shrink happening here. What we can do now is some properties of inequality. I can multiply everything in this inequality by x squared. So that's going to give me negative x squared less than or equal to x squared times sine of 1 over x less than or equal to positive x squared. So I started by saying sine of 1 over x must be trapped between negative 1 and 1. I multiplied all of the sides by x squared using the multiplication property of inequalities. Now, what I really care about in this problem, so I have what I wanted to have here, except I'm missing the limit. So the limit of all of these things, I'm going to take the limit as x approaches 0 of each side. So I'm going to take the limit as x approaches 0 of negative x squared. This will still need to be less than or equal to the limit as x approaches 0 of x squared sine of 1 over x. This will still be less than or equal to the limit as x approaches 0 of x squared. And you may be starting to think, yes, we started with something that made sense, but how is this helping us? Well, if you look here, you can evaluate this limit. The limit as x approaches 0 of negative x squared, you can use direct substitution there. That's going to give you 0. That means we know that this middle limit has to be greater than or equal to 0. Now, if you look at the top piece, this limit we can also evaluate using direct substitution, and that's also going to give me 0. So what we've just done is we've said, I don't know what this limit is, but I know that it's trapped between 0 and 0, which means, therefore, this limit, the limit as x approaches 0 of x squared sine of 1 over x, this limit must be equal to 0 by the squeeze theorem. Since we said it must be trapped between 0 and 0, that in fact means that it must be 0. So let's recap what we covered in this lesson. The first thing we talked about are the three most important trig limits to remember. We talked about the limit as x approaches 0 of sine of x over x is 1, as is the limit as x approaches 0 of tangent of x over x. We also talked about the limit as x approaches 0 of 1 minus cosine of x over x. That must be 0. We talked about how to use those three special important trig limits to manipulate other trig in order to be able to use those properties and find the limit when we get indeterminate form. We went through a lot of examples and we reminded ourselves that we should always check for direct substitution first. Then, from last lesson, we talked about factoring and conjugates. If those two things don't work, then we're looking at trig and trying to see if we can manipulate this to use one of our three trig identities. Lastly, we wrapped up by talking about the squeeze theorem and how if we can't find the limit using things that we know, we may be able to trap it in between two limits that we do know, which could result in us actually finding that limit. So post any questions that you have below or shoot me an email, and I look forward to supporting you on this in class. Thanks for listening.